Welcome to the deep dive. Today, we're staring into, well, a cosmic looking glass, exploring the genuinely mind-bending idea of a CPT-symmetric universe, what some folks are calling the Antiverse. And forget science fiction for a moment, this is actually a serious theoretical framework rooted in fundamental physics. And what's really wild is that it makes predictions we might actually be able to test.
Exactly. We're not just, playing with hypotheticals here. The sources we've looked at suggest this could be a potentially real counterpart to our own universe. Not just a shadow, but like a fully formed other half of space-time.
A twin universe. Wow.
Yeah, think of it like the universe having a twin.
Okay, so what does CPT-symmetric actually mean? Let's try and unpack this a bit.
Right.
Imagine every sort of fundamental aspect of our universe, things like electrical charge, the arrangement of objects in space, which is parity, and the direction of time, they all get flipped simultaneously. It's like a triple cosmic backflip happening all at once. We're talking charge reversal, a mirror image in space, and time running backward relative to us all rolled into one.
And this isn't just some, neat mathematical trick they came up with. The implications, well, they ripple through our understanding of basically everything.
Like what?
Like the Big Bang, the whole enigma, black holes, even the ultimate fate of the cosmos.
Yeah.
Get ready for some serious perspective shifts, I think.
Absolutely. So our mission today is really to get to the heart of this CPT-symmetric universe theory. We want to understand its core ideas, what it means for, well, our current view of reality, and maybe crucially, how we might actually go about finding evidence for it.
Yeah, nail down the testable bits.
Right. Our aim is to give you a clear, hopefully engaging picture without getting too bogged down in, complicated equations.
Okay, so let's start with the Antiverse itself. It's really crucial to grasp that this isn't just an idea on paper.
Not just math.
Not just math. The theory proposes it as a physically real counterpart to our own universe. The key insight here is that it's not just different. It's a mirror image in these really fundamental ways.
Think of it as a true second physically complete half of space-time, as one source put it.
Exactly.
And these differences are, well, they're profound. Take time, for instance. In our universe, time moves forward, right? Like a river flowing one way.
RGO.
In the Antiverse, time also flows forward for anyone living there. But from our viewpoint, that river is flowing backward.
Right. Relative to us, their time is negative.
Yeah.
They exist in what we consider the time before the Big Bang.
Wow. Okay. And then there's charge, where we have, the building blocks of matter, protons, electrons, those little left-handed neutrinos.
The Antiverse has their exact opposites. Antiprotons, positrons, and technically right-handed antineutrinos. The fundamental electrical properties are flipped.
Okay. And a concept called baryon number, which basically just counts up how much normal matter, like protons and neutrons there is. That's reversed too.
Yep. Our universe has this huge positive baryon number, something like 10 to the 78. Massive.
Unimaginably big.
Right. The Antiverse would have an equally huge but negative baryon number. So the total for the entire two-part system.
Zero.
It's like the universe has to balance its books.
Yeah.
Very tidy.
Yeah.
What's also fascinating is something called the C-key phase. It's a bit technical, but it governs how some particles interact, and it's related to why we have more matter than antimatter.
Okay.
The specific values of these phases in our universe would be exactly mirrored, basically, negated in the Antiverse. It points to this really deep level of symmetry in the fundamental rules.
Even dark matter, right? That mysterious stuff making up most of the mass.
Yeah.
That gets a CPT twist, too.
It does. The theory points to a specific type of heavy right-handed neutrino as a stable dark matter particle. Now, here's where it gets really interesting. Because of the CPT flip, particularly the charge part, this particle is its own antiparticle.
Wait, what?
Yeah. So the dark matter particle over there in the Antiverse, it's exactly the same particle as ours. Their anti-dark matter is just more dark matter, the same stuff.
Okay, that's weirdly symmetrical.
It is, and it naturally leads to a crucial question.
Yeah.
Is the Antiverse essentially the same as ours in any meaningful way? I mean, apart from these flips?
Right, like fundamentally.
And the answer, according to the theory, is a resounding yes when it comes to the actual laws of physics. Think of it like that reflection again. The image looks the same, but everything's just oriented differently.
Exactly. The core equations that govern, how particles interact, that's the standard model, and how gravity works, Einstein's general relativity, they remain unchanged under these CPT operations.
So the rule book is identical.
The rulebook is identical in both universes.
And when it comes to what they perceive as matter and antimatter, Well, it's all relative to their own universe, what we
Okay.
call a proton. An inhabitant of the Antiverse would just see it as a normal fundamental particle making up their world. Their entire reality would be built on what we would label as antimatter. But for them, it's just matter.
Just normal stuff.
Just normal stuff.
And the history of their cosmos. It would mirror ours, but in reverse.
Exactly. Just as we see the universe expanding and cooling from a hot, dense state after the Big Bang,
Yeah.
they would see their universe doing the same thing, expanding and cooling, but heading towards that hot, dense state, which is TDO for both of us, in their forward time direction.
So both sides would experience the same sequence of cosmic events, like radiation dominance, then matter, then dark energy relative to their own timeline.
Precisely. It's vital to understand that the Antiverse isn't just some slightly tweaked version of reality. It's fundamentally the same in its laws, but flipped in its basic properties like charge and time direction relative to us.
And this isn't just a quirky idea someone had. Our sources emphasize that without this antiverse, a really fundamental symmetry of physics called global CPT symmetry, well, it would be broken.
Which physicists generally don't like. Broken fundamental symmetries make us uncomfortable.
Right. And as research has shown, the existence of the antiverse might actually help us solve some huge puzzles about our own universe.
Like what?
Like why there's more matter than antimatter around us, the baryon asymmetry problem. And it could also potentially explain the amount of dark matter we observe.
So it's not just fixing a symmetry problem. It might actually explain things we see.
Exactly. It's like the antiverse is this missing piece that helps the whole cosmic puzzle fit together more neatly.
Okay. So if this CPT-symmetric universe is real, what would it actually be like over there in the Antiverse? What kind of cosmic stuff would be happening?
Well, in their very early times, right? Just after their version of the Big Bang, which is our T0 moment.
Their beginning?
It would have been this scorching hot soup of antimatter particles, so positrons instead of electrons, antiprotons instead of protons, and so on, along with photons and antineutrinos.
So Big Bang nucleosynthesis, the process that made the first light elements.
Would have happened there too. But using antimatter building blocks, they'd end up with antihelium, antilithium.
And a huge number of antibaryons, that negative 10 error worth.
Right. Then, as their universe aged, just like ours did, gravity would take over.
Clumping things together.
Exactly. Antimatter would clump together to form anti-galaxies full of anti-stars.
Which would live and die, presumably, just like regular stars.
Yeah, you'd get anti-supernovae, anti-neutron stars, anti-black holes. The key insight here is that the large-scale structures would probably look remarkably similar to our own universe, just made of the opposite stuff.
And the amazing thing is, their entire field of astrophysics would basically mirror ours.
How so?
Well, they'd observe the same kinds of electromagnetic radiation, light, radio waves, etc. They detect the same kinds of gravitational waves from merging anti-black holes or anti-neutron stars.
They might even detect anti-cosmic rays, right? High-energy antiparticles zipping through their space.
Precisely. The only difference at a really fundamental microscopic level would be that inverted CP phase we mentioned.
Which would cause some subtle differences in particle interactions.
Yeah, like in radioactive decay, positrons might play the role electrons do for us, and vice versa. But macroscopically, very, very similar.
And what about the very distant future? We think our universe is heading towards this cold, sparse state dominated by dark energy.
The heat death scenario or something like it.
Yeah. Does the antiverse face the same fate?
In their forward direction of time, yes. Their distant future would look exactly the same. An accelerating, sparse, de Sitter-like universe. It's a completely symmetrical long-term fate for both universes.
Which naturally leads to a really profound question. If the antiverse is so similar, could we ever, like in principle, tell them apart from us? Just by looking around within our own universe.
Locally, just doing experiments here on Earth or looking at nearby galaxies, the theory suggests it would be impossible. Because any local experiment we could perform wouldn't be able to determine if we're in the matter universe or the antimatter universe. The fundamental properties, charge, parity, time perception, are all reversed together relative to the other side. It's like trying to tell if you're looking at a photograph or it's negative without having the original for comparison. You can't tell from just one.
Okay, so locally, no dice. But globally, looking at the whole picture.
Globally, the entire CPT-symmetric system, our universe plus the Antiverse, might have some unique fingerprints.
Yeah.
Things that arise from the fact that it's a combined system.
Like what kind of fingerprints?
For instance, that total amount of normal matter, their baryon number, across both universes should add up to 0.
Okay.
There's also a prediction about the overall CP phase of the combined system being 0. And, maybe most importantly, it predicts a very specific fundamental state for the universe, the quantum vacuum state.
And these could leave subtle imprints on our cosmos that we could potentially detect.
That's the hope. Specifically, the theory predicts 3 key global markers. First, we should not see strong evidence of primordial gravitational waves generated by cosmic inflation.
Inflation being that hypothetical period of super rapid expansion right after the Big Bang in the standard model?
Exactly. The CPT model doesn't need inflation, so it predicts these specific gravitational waves should be very, very weak or absent. There's a number called R, the tensor to scalar ratio, and this theory predicts R should be tiny, like less than 10 here.
Okay, marker 1, basically no inflationary gravitational waves. What's marker 2?
Marker 2 is a very specific prediction for the sum of the masses of the 3 known types of neutrinos. It pegs it right around 0.06 electron volts.
Wow. That's precise, not just an upper limit, but a specific value.
A specific value, yeah. It comes out of how the CPT symmetry helps select the vacuum state.
And marker 3?
Marker 3 involves subtle patterns in the oldest light in the universe, the cosmic microwave background, or CMB, specifically patterns of non-Gaussianity. The CPT model predicts a unique signature here related to the shape of the initial fluctuations.
So these 3 things, the lack of strong tensor modes, the specific neutrino mass sum, and the unique CMB pattern, these are the crucial tests.
They really are. If our observations definitively contradict these predictions, like if we find strong evidence for inflation, or measure the neutrino masses to be very different, or see a different pattern in the CMB, it would strongly suggest that the Antiverse, at least as this perfect CPT mirror, might not exist.
These are the clues we need to look for in our universe to potentially glimpse its hidden twin.
Exactly. They're the potential cracks in the mirror, so to speak.
This really makes you wonder, though, is this antiverse idea just a clever mathematical trick? A way to make the equations look nice and symmetrical? Or does it reflect some deeper physical reality?
That's a fundamental question, isn't it? What makes this more than just a neat thought experiment? Well, our sources delve into this. They explain that when you try to describe the very beginning of the universe, the Big Bang, using our best theories, quantum physics and general relativity, you run into this massive problem called a singularity.
A point of infinite density, infinite curvature, where the physics breaks down.
Exactly. It's mathematically problematic and physically nonsensical. The idea of CPT gluing our universe to the Antiverse at TO0 provides a way to actually smooth out this singularity.
Oh.
By imposing this CPT symmetry as a boundary condition, the math becomes regular, well-behaved. It essentially removes the infinite curvatures and, as a bonus, might uniquely select the correct vacuum state for the universe, solving another long-standing problem.
So the Antiverse isn't just tacked on for fun. It's presented as like a necessary part of making the whole picture mathematically and physically consistent, especially at the very beginning.
That's the argument. Without it, you're left with this unresolved singularity at the beginning of time and ambiguities about the fundamental state of empty space, particularly in the far future.
Yeah.
The CPT structure potentially resolves all of that.
Okay, I can see the theoretical appeal. Now, for the really mind-blowing question, could there ever be any way to make contact between our universe and the Antiverse?
The communication question.
Yeah. Could information, or maybe even something more tangible, cross that TO boundary?
Well, the standard view in physics has always been pretty clear. The Big Bang singularity, that TO moment, is a boundary in space-time that nothing can cross, at least not without exceeding the speed of light, which is a no-go. It's like a point of no return in both time directions.
Impassable.
Traditionally, yes. Impassable for particles, energy, anything traveling locally.
But I sense a but coming.
But
yeah.
Some fascinating theoretical work, particularly looking at things through the lens of quantum field theory and path integrals, suggests there might be subtle connections across this boundary.
How so? What kind of connections?
It's not about sending particles through. Exchanging things like photons or W and Z bosons or gluons, the standard force carries, that seems impossible. It would violate basic principles like causality.
Okay, so no sending radio signals back and forth.
Probably not. However, the theory hints that subtle quantum correlations, especially in very, very long wavelength fluctuations of certain fundamental fields, maybe scalar fields or even gravity itself, might be able to transmit some kind of information across the TO0 surface without locally breaking the speed of light limit.
Quantum correlations, like entanglement, but across the Big Bang.
Sort of analogous, yeah. It's highly theoretical, highly speculative. We're talking about correlations in the phases of quantum fields that could potentially persist across that boundary. It's not sending a message like an email, but maybe encoding information in the very fabric of space-time itself.
Wow. That opens up some incredible, if very distant, possibilities.
It certainly does.
Okay, this leads us to another really radical implication. What this CPT-symmetric universe might mean for the ultimate destiny of the cosmos. You mentioned earlier it might not be heading towards that final cold heat death.
That's correct. That's one of the most profound potential consequences. In the standard cosmological model, the CDM model.
Lambda called dark matter, yeah.
Right. The universe is predicted to become increasingly disordered over time thanks to the second law of thermodynamics. Entropy always increases, heading towards this final state of maximum entropy, maximum disorder, where no more useful energy can be extracted. Everything just cools down and spreads out forever. The heat death.
Bleak.
A bit bleak, yeah. But the CPT framework offers a dramatically different picture. It suggests that the overall entropy, the disorder of the combined system, our universe plus the Antiverse, was actually at a minimum at the Big Bang, at TCOZO, that joining point.
A minimum, so maximum order at the start.
For the combined system, yes. From that central point, entropy increases in both time directions forward in our universe and forward, which is backward for us, in the Antiverse.
Okay, so disorder increases away from the Big Bang in both halves.
Correct. However, crucially, this increase in entropy isn't unlimited, it's bounded. There's a maximum amount of entropy the universe can hold related to the accelerating expansion driven by dark energy, specifically the area of the cosmological event horizon.
The de Sitter horizon.
Exactly. So, unlike the traditional view where entropy just goes up and up forever, here it approaches a finite limit. There might not be a final state of complete stagnation.
And the role of that de Sitter horizon, the edge of the observable universe in the far future, that's different too.
It is. In the standard model, the horizon has this incredibly tiny temperature, the Gibbons-Hawking temperature, maybe 10 Euro-Kelvin, almost absolute zero. It's seen as a dying ember.
Right.
But in the CPT view, this constant faint background temperature isn't just a relic. It represents a continuous source of subtle free energy, a perpetual quantum fluctuation bath.
So the universe never truly gets cold and dead.
Potentially not. And where the standard model predicts that the universe will eventually run out of information capacity, Fisher information, the CPT universe suggests it remains finite, even gravitational fluctuations.
Yeah.
In the standard CDM model, they're expected to decay away exponentially as the universe expands. But in the CPT picture, because of the connection across T0, they might persist in a more subtle logarithmic form. The universe might keep chattering gravitationally.
Implying a more dynamic long-term evolution.
Exactly.
Okay, let's look at the timeline then, the really distant future. How does the CPT story differ from the standard one?
Well, for the first, say, 10 fit into 10 Euro years, things might look broadly similar. Stars burn out, leaving brown dwarfs, white dwarfs, neutron stars.
The degenerate era.
Right. But even here in the CPT view, that faint de Sitter radiation background, that 10 Euro K temperature, starts to dominate local heat exchange more significantly than in the standard picture.
Okay, what happens next? Black holes evaporating.
Yeah, somewhere between 10 and maybe 10 years, black holes are expected to evaporate via Hawking radiation. In the standard model, this is thought to be a purely thermal process that destroys information.
Right, the information paradox.
But in the CPT view, these aren't standard black holes with singularities. They're potentially these black mirrors.
Black mirrors.
Yeah, the idea is they don't have a singularity. Infalling stuff might interact with time-reversed anti-partners near the center due to quantum effects, preserving information. The Hawking radiation they emit might not be purely thermal. It could be a kind of bounced CPT transform mode carrying correlated information back out.
So information isn't lost.
Potentially not. It suggests a unitary evolution, which quantum mechanics likes. The radiation might have a long quantum tail in its spectrum, a subtle signature.
Okay, fast forward even further. Beyond 10 years, standard model predicts darkness, cold gas.
Pretty much. A near-empty void, maybe a diffuse gas at around 10 Kelvin, but utterly cold and dark.
But the CPT universe suggests something different.
First, you'd still have that constant, faint glow of photons from the de Sitter temperature, around 10 kK. Second, if the heavy neutrino dark matter exists, it would still be decaying very, very slowly, continuously producing a trickle of ultra-high energy neutrinos, maybe EeV scale, a faint cosmic ray background that never quite goes away.
So not complete silence.
Not complete silence, and perhaps most remarkably, beyond timescales we can barely conceive. Where the standard model predicts true, final heat death, the CPT universe hints at ongoing activity.
Like what?
Quantum fluctuations at the de Sitter horizon could occasionally, very rarely, give rise to new structures, maybe tiny Boltzmann brain-like accretions, or even mini black mirrors popping into existence and evaporating.
Whoa!
And phase transitions in the vacuum itself might continue indefinitely, albeit on incredibly long, perhaps exponentially increasing timescales, like the universe occasionally resetting itself in small ways.
So in essence, the CPT universe paints a picture where that relentless drive towards increasing disorder, the second law, doesn't lead to a final dead equilibrium state.
That seems to be the implication. The fundamental CPT symmetry and the properties of the de Sitter horizon act like a kind of cosmic thermostat and boundary condition that prevents true equilibrium. There's always this subtle level of activity, a cosmic hum of quantum fluctuations, maybe logarithmic chatter.
It never truly settles down.
It seems not. The de Sitter entropy is finite, maybe 10-unit Ausable bits, but the horizon acts as both a source and a sink, maintaining a gradient. Black mirrors preserve coherence. There's no true global vacuum state to fall into.
So what remains alive on these almost infinite timescales?
We'd have the random creation and evaporation of mini black mirrors. You'd have these faint bursts of high-energy neutrinos from dark matter decay, perhaps with a timescale around 10 years or longer. You'd have those persistent, subtle scalar and gravitational fluctuations, maybe growing logarithmically with the scale factor, and potentially gravitational echo rings from the evaporating black mirrors carrying information.
It's not a silent graveyard then? It's more like a subtle, infinitely stretched out, I don't know, quantum jazz jam session. Huh. That's a great way to put it. A subtle, infinitely stretched jazz jam of quantum variations. Not heat death, but maybe heat persistence.
Okay. If this CPT-symmetric universe is actually how reality works, the philosophical and maybe even technological implications are just staggering.
Oh, absolutely. It forces us to rethink some of our most fundamental assumptions about, well, everything.
Like causality.
Yep.
You mentioned earlier the Big Bang might be influenced by the future.
Exactly. If T0 is this two-sided mirror connecting our universe and the Antiverse with opposite time directions, then events near the Big Bang could, in principle, be influenced by conditions from both our future and the Antiverse's future, which is our past.
That sounds like destiny almost, or predetermination.
Maybe not quite destiny, but it suggests a much more interconnected, holistic view of cosmic history, like the universe optimizing its entire path through time, forwards and backwards. Some call it a double Moss principle, where the global state influences local physics. It certainly challenges our simple linear view of cause and effect. And it could imply that the initial conditions of our universe weren't just random chance or fine-tuned by inflation.
Precisely. They might be fixed by the requirement of CPT symmetry with the Antiverse. The fine-tuning problems of inflation might just disappear, replaced by this fundamental symmetry. It could even lead to a new way of thinking about quantum measurement, involving interference from both past and future states.
Mind blown. Okay, what about technology? You hinted at some far-out possibilities.
Highly speculative, of course. But if this physics is real, imagine harnessing those heavy neutrino decays. Could you build, like, neutrino beacons for communication across galactic, maybe even intergalactic distances? They decay so slowly that the signal would persist.
Okay.
Or what about those black mirrors? If they reflect quantum information coherently, could you build gravitational waves lasers based on reflection from them? Or maybe use their unique radiation signature to somehow accumulate energy, enhance plasma heating.
Gravitational wave lasers.
And if those subtle vacuum fluctuations have a preferred orientation due to the CPT structure, could you use them for phase navigation, defining an absolute time orientation across the cosmos?
These sound like science fiction plot devices.
They do now. But the underlying physics, if correct, might allow for things we can't yet imagine.
Are there any more local effects, things we could actually search for, maybe even soon, beyond those three big cosmological markers?
Yes, potentially. Those gravitational wave echoes from merging black holes at their black mirrors, they might produce specific echo patterns after the main signal. LIGO, Virgo, future detectors could look for those.
Okay, echoes. What else?
We could look for subtle shifts in the spectral lines of hydrogen from the very early universe, the 21-centimeter line from the cosmic dawn, around redshift 30. The specific CPT vacuum state might leave a faint imprint there. That's called relic vacuum spectroscopy. And related to the CMB non-Gaussianity, the CPT model predicts a specific absence of certain vacuum ambiguities, called alvacua, that could exist in a standard de Sitter space. This leads to a prediction that a specific pattern, called FNL equilateral, should be close to zero. Future CMB missions like Lightbird will test this.
So specific signatures in gravitational waves, early hydrogen signals, and CMB patterns. Testable things.
Testable things, yes.
Okay, let's talk about the boldest speculation mentioned in the sources. This idea of chatting across the Big Bang.
Ah, yes, the ultimate long-distance call.
How would that even work? You said particles can't cross.
Right, no particles.
Right.
But remember those long wavelength quantum fluctuations.
Mm-hmm.
The idea proposed in some of the research is that if you could somehow manipulate the phase of a very long wavelength scalar field now on horizon scales,
Okay.
the manipulation that encoded information due to the CPT connection at TO0 could manifest itself as specific initial phase conditions for that same field in the Antiverse's past, which is our future direction from T0.
So we wiggle a field here, and it appears as an initial condition over there.
In a highly correlated way, yes. It's not sending a beam, it's more like setting the initial conditions for their universe based on actions in ours. The energy requirements would be absolutely astronomical planetary scale or beyond to influence modes on the scale of the horizon.
That if you could do it.
If you could, the potential rewards are immense. Absolute timekeeping across universes. A way to archive information that survives the end of our universe, appearing at the beginning of theirs. Maybe even, eventually, establishing some kind of two-way metagalactic communication protocol.
That is profoundly strange and wonderful. The sources even included a kind of fictional narrative to illustrate this, didn't they?
They did, yeah. A sort of what-if story called Whispers Behind the Mirror.
Right. It involved a future research station, Search Z, detecting this weird ultra-long wavelength signal.
Yeah, a phase echo in a scalar field.
Yeah.
It had a specific frequency and a contour that looked like what you'd expect from a CPT-symmetric black mirror horizon, but vastly larger than any known black hole.
And the signal was encoded, right? What was the message?
It turned out to be the first part of pi, but encoded in a base 3 system that, in the story, was invented after the signal would have had to have been sent from the Antiverse.
Implying it came from their future, which is our past relative to them or something. It's confusing.
Exactly. A committee of 2 times is formed, and they conclude it's artificial, sent from the Antiverse before their Big Bang, RT0, from their perspective.
So humanity decides to reply. Project Echo 2.
Yep, generating an even longer wavelength wave, needing massive energy. Then there's this hypothesis by a scientist, Anna Levina, that some physics-obsessed civilization in the Antiverse deliberately pre-encoded a message in their past mirror, knowing it would appear in our future.
And the full message wasn't just pi.
Pi was just the header. The rest was like super detailed annotations of the initial conditions of the CMB, the fluctuations, almost like pointing out, we were here, we set this up, including a subtle logo, a golden ratio spiral, hidden in the quadrupole moment.
Whoa, okay. And then?
The final part of their message proposed a way to avoid the heat death, creating a correlated chain of mini black mirror holes on the scale of galaxies to extract energy from the de Sitter horizon indefinitely. A joint project between universes.
A cosmic engineering proposal.
Basically, yeah. So Search Z sends the reply signal, and the story ends with a new, shorter period blip detected, interpreted as challenge accepted, begin symphony.
Suggesting the start of this coordinated effort between the two universes. Wow. Okay, great illustration, even if fictional.
Definitely puts the implications into sharp focus.
All right, let's step back from the fiction now and do a more systematic breakdown of the actual scientific CPT mirror hypothesis. Where did this idea really come from?
As we touched on, it fundamentally comes from trying to resolve the singularity problem in cosmology and black holes by applying global CPT symmetry. The idea is to glue space-time together at the singularity in a CPT-symmetric way.
And it's economical. It doesn't require lots of new particles or forces.
Remarkably so. The core model really only requires the standard model of particle physics plus 3 right-handed neutrinos. These are already suspected to exist to explain neutrino masses. One of these right-handed neutrinos naturally becomes a stable dark matter candidate in this framework.
So, standard model plus 3 neutrinos. That's it.
Pretty much. Which is quite appealing compared to, say, inflation models that often require new scalar fields, or string theory with its extra dimensions and particles.
And the motivations, again, just to be clear.
The big ones are avoiding the Big Bang singularity, avoiding black hole singularities, potentially solving the black hole information paradox, avoiding the need for cosmic inflation to explain flatness and isotropy, providing a mechanism for baryon asymmetry, matter over antimatter, predicting dark matter, and solving the vacuum selection problem in quantum field theory. It tackles a lot of big issues.
Okay, let's quickly recap the cosmology of this CPT Big Bang. No inflation needed.
Correct. Flatness and isotropy aren't explained by a burst of expansion, but by the universe being a mirror image of a pre-existing contracting phase, the Antiverse.
And the verification for that is?
The absence of those detectable inflationary tensor modes, that very small value, Virga. Current limits are compatible, but future experiments will push this much further.
Density fluctuations, the seeds of galaxies.
They rise from scale-invariant vacuum fluctuations across the TiVo boundary. The verification is matching the observed CMB power spectrum precisely, and specifically not finding significant non-local types of non-Gaussianity, like large FNL equilateral or orthogonal. Lightbird will be key here.
Neutrinos and dark matter.
CPT fixing the vacuum leads to that specific prediction for the sum of neutrino masses, a min 0.06 eV. This assumes a normal mass hierarchy with the lightest neutrino being nearly massless.
And the test.
Upcoming neutrino experiments like Catron upgrades, neutrinoless double beta decay searches, and future cosmological surveys aim to measure min down to maybe E.02 eV by around 2029. That could rule this prediction in or out. The dark matter particle is that heavy, stable right-handed neutrino, may be detectable via indirect signals in telescopes like IceCube Gen 2.
Baryon asymmetry, matter versus antimatter.
Global baryon number B is 0, but each half gets a non-zero B, positive for us, negative for them, due to how fermion wave functions reflect across the TPO boundary. This is linked to CP violation in neutrinos, potentially testable via neutrinoless double beta decay.
Okay. And the black mirror concept replacing black holes, just quickly again.
No singularity inside. In-falling particles effectively annihilate with their CPT-reversed anti-partners arriving from the other side due to quantum fluctuations near where the singularity would be. Hawking radiation isn't thermal information loss, but a bounced CPT mode preserving quantum information unitary evolution.
So where do we stand right now experimentally with these key predictions?
Tensor waves are. Current limits from Planck and Biassy Peacock are compatible with the CPT prediction, R 0.036, while CPT needs R 10 EO. Future CMB missions are needed. Some of neutrino masses, current limits, around 0.09 eV from cosmology, are compatible with the 0.06 eV prediction. Getting tighter. Heavy O, dark matter. No direct or definitive indirect detection yet. Future high-energy neutrino telescopes and maybe particle colliders could probe the relevant mass range, predicted around 4.8 pi 10 very heavy. Gravitational wave echoes. Searches have been done, but no statistically significant detections confirmed yet. Needs more data and better sensitivity.
Okay, so summing up the strengths of the hypothesis.
Highly compact theory addressing multiple fundamental problems simultaneously. Makes firm, falsifiable numerical predictions, R-AMPI-FNL. Avoid singularities without invoking full quantum gravity, which we don't have yet. Mathematically elegant.
And the weaknesses or main criticisms.
The precise origin and spectrum of the scalar perturbations needs more development, though models exist. The idea of a global boundary condition at TO might seem unnatural to some compared to local physics. Lack of definitive echo observation so far, and some argue the CPT explanation for the low entropy start is just relabeling the initial conditions problem, though calculations do show the CPT solution appears to be a preferred saddle point in the path integral formulation.
Any final intuitive analogy? You mentioned the optical mirror.
Yeah, or think about the Kruskal-Sekeres coordinates used to describe standard black holes. They mathematically extend space-time through the singularity to another region. The CPT model makes that other region physically real and CPT mirrored.
So your final assessment, where does this hypothesis stand today?
It's currently permissible by data, but definitely not proven. It offers very compelling theoretical advantages. The crucial tests are really coming online in the next 5-10 years. CMB, neutrinos, gravitational waves. Its strength is its falsifiability. If those predictions fail, the model is in serious trouble. If they hold up, well, the implications would be truly profound. It's a high-stakes game.
So there you have it, our deep dive into this genuinely mind-bending concept of a CPT-symmetric universe, an antiverse mirror twin to our own.
Yeah, it really forces you to reconsider, well, everything you thought you knew about time, space, matter, and the cosmos itself.
And as we've hammered home, this isn't just, philosophical navel-gazing. There are concrete, testable predictions.
Exactly. Those primordial gravitational waves, or lack thereof, that specific sum of neutrino masses, those potential gravitational wave echoes from black mirrors.
And the time frame for potential verification or falsification is actually pretty soon, within the next decade or so.
It really is. Results from experiments like LIGHTBIRD, Katrin, IceCube Gen 2, next-gen gravitational wave detectors, they can give us real answers. So definitely keep an ear to the ground for news from cosmology and particle astrophysics.
It really makes you wonder, doesn't it? This idea that our universe might just be one half of a much larger, perfectly balanced CPT-symmetric system joined at the very beginning. That framework, it just invites a total reevaluation of causality, of initial conditions, maybe even our place in the grand cosmic narrative. Are we co-creating the beginning with our mirror image?
It's a provocative thought. Perhaps the ultimate provocative thought for today is this. If the CPT universe is real, maybe the beginning wasn't a moment of pure randomness, but the most ordered, most symmetric state possible, from which complexity unfolds in two opposite temporal directions. A cosmic seed crystal.
Wow, okay. Well, we definitely encourage you to delve deeper into the research papers if you're interested and keep exploring this fascinating frontier of cosmology.
The universe, it seems, is always stranger and more wonderful than we imagine. And the possibility of a mirror twin. Well, that's about as strange and wonderful as it gets.